Okay, so let's solve the remaining two problems of weekly contest 426. Maximize the number of target nodes after connecting trees. There exist two undirected trees with n and m nodes with distinct labels in ranges 0 to n minus 1 and 0 to m minus 1 respectively. We're given a two integer arrays edge 1 and edge 2 of lengths n minus 1 and n minus 1 respectively, where edges 1i equals to ai bi indicates there is an edge between nodes ai and bi in the first group, and edges 2i equals to ui bi indicates that there is an edge between nodes ui and bi in the second group. You're also given an integer k. Now u is the target to the node v if the number of edges on the path from u to v is less than equals to k. Note that node is always a target to itself. We have to return an integer array answer, but answer is the maximum possible number of nodes target to the node of the first tree if you have to connect one node from the first tree to another node in the second. And there is also an important note given that queries are independent of each other, which means suppose you connect zero node from the first tree to the first node of the second tree, then for the next intersection, you can connect 0 to any other nodes of the second tree. After erasing the connection of 0th node of the first tree to the first node of the second, I would explain this. Let's see the constraints. Everybody's 1000. So let's understand this problem. I'm taking an example. This is my tree 1, this is my tree 2. This is an edge query I have connected the 0th node of the tree 2. So one approach I can think of is there are n nodes here, n nodes here. Brute force, I can do every connection for the n. But this one node, I have m connections. For every node, I would have m possible connections and take out the max out of all of them after calculating the distance k using BFS. So this would require time complexity of O n to m for all the possible connections possible, and this is for the BFS for the condition given that the distance should be at most k. So this would be the time complexity for brute force approach. As our n and m are 10 cube given in the question, maximum. This would not satisfy our constraints. This would become in power 9. So this will not satisfy all the test cases if we use the brute force approach. So I'm going to think of an optimal approach. One thing I can see is that if I do some pre-cam computations in trees 1 and 2 before attaching them, that would significantly reduce my time complexity by a lot. Going in this method of thinking, I would just do BFS on every node and count how many nodes are at a distance of k from each node in this tree, and same for each node in this tree. Here I would find out k minus 1 distance nodes. Because after attaching this, I would get an extra edge from here. So from this, the distance would be k. which is what we need. The maximum distance should be key. So separately, I would apply BFS. First on this tree, then on this tree, then I can join. That would not match. BFS would require O of n here at the max and O of n here at the max. So time complexity will be reduced to n plus n into k. Not even into k, n plus n. Rest is just counting the max nodes. Here the queries are independent. That is why here the queries are independent. That is why I can use greedy approach. Like I have to calculate the maximum possible target node possible from each node in the T1. So I can calculate the maximum from here, max number of adjacent nodes at k minus distance from source node U. There would be one source node go out of these four. Should have the maximum distance of k minus, maximum number of nodes at a distance k minus 1. So every time for each node we attach every node from the secondary, there would be a case where we attach it from the maximum number of adjacent one source node. So that would give us our answer for every case. For every node here, we could just simply get out the max out of the secondary nodes and sum it up with the possible adjacent nodes of the nth node here at a distance of k from this node. That would give us a better answer. Out of all the variants of target from two, one of them would be max, which is what we require. And take it. So let's forward up this would help in visitor array marking. Let's write even as edges, right? E2 as edges 2. From collection, I will import tag queue as I will be using it in BFS. Node 1 number of nodes in tree 1 would be length of 1 plus 1. Node 2 number of nodes in 2 pivot 3 length of 2 plus 1. Now I would create active principles for the would be as follows. Okay. So that just means so this would be my two adjacent sequences. Now I will write these queries given in the pen adjacent one US source BS system versus also true as this is an undirected tree. So just populate. Same goes for the second graph, secondary edges of a thin edges straight of eight of the pen here. Now I will write the EFS function and process features and sequence starting and the max distance possible. T1 would give me count of PFS with max distance as K for node range node 1 first row. It will give counts of PFS adjacent to node K minus 1 max distance for node M range node 1. Max would give me max of T2 as we earlier saw that 3D approach here works because of this queries are independent from each other statement. So let's populate our answer. Yes. Now at the very last, finding this PFS function. Initializing text. With the starting node given to us. So I will end it with start and 0. Because the initial distance from itself will be 0. This for counting neighbors at a distance, max distance of k minus 1. So while my queue is not empty, I will pop the leftmost one. If it's not in this and distance is less than equals to max distance, then only I first mark it visited, increment my count because it's less than max possible value, k minus 1. And now for neighboring nodes of this node which we extracted, I would append all of them and increment the distance by 1. Lastly, I will return down. So let's check for mistakes. Nothing is set for now. Let's now see if it's passing all the test cases. Yep, it does. So this was our third problem. Let's solve the last problem of the challenge was assignment. Maximize the number of target nodes after connecting trees. So this is the second part. Yes. There exist two undirected trees, same as the previous question. So I'm not repeating that. This is also same as the previous question. From here, the difference is starting. Let's read it out. Node U goes target to node B if the number of edges on the path from Q to B is even. Note that node is always target to itself. Return an array n of integers answering answer is the maximum possible number of nodes that are target to node I of the first tree if you have to connect one node from the first tree to another node. So here the condition is that um, there should be an even number of edges between the start node and the end after connecting with both the. Here also the same condition of the variables is given. They are independent of each other. Constraints are given as okay, so here constraints are even more variables. But still our solution could work because we calculated an order of n plus n solution. Just we have to take into account this new condition instead of the max k node. Let's solve this problem. So this is a question. N equals to 5 here, n equals to 3 here. This is the example I feel. The brute force approach would be again the same as the previous one. I would just connect each node with every other node in the tree and then calculate the distance from one the source tree to every other tree in the every other node in the combined tree and check for um, edges value is even through BFS. So it would again be a solution of time complexity as order of n into m, n plus m, which would definitely not satisfy our constraints, as it is given in the question that n and m are of the order 10 raised to power 5. So for def, now we would use bipartite graph condition here because it's given in the question that even number of edges should be there between source and destination. So only we have to check for the parity. Nothing else. Starting the base as our root node, I would assign red and blue alternatively to every other node using BFS to both the trees. They're also equivalent to levels. This is all the even levels would have R as their placeholder, and all the odd levels would have blue as their placeholders. So if like I don't have to code using R and B in the um, implementation, I could just use the odd even parity check. That would simplify the code a bit, but it's the same, one and the same. Checking for even odd or using the R or B. So what I'm gonna do is, suppose I connect these two variables. From this, I need to find out max target nodes from this overall tree an even number of edges. So one would be this, and this. One. Second would be this. Third would be this. And fourth would be this. So total 4 I got as answer. Now I would check from an order. Connect these two. Give us 4. Now I would connect this B with 0. It's I. Again, I have to do the same thing. Check for even. In this case, it would not be possible here. All the blue ones would be at an even distance. This one and this two. So 4 for this one, 2 for this one. From this example, I can see a pattern like there are 2 odd parity nodes in the tree too at level 1. Odd parity and 1 even parity node. So I would take out the max of these two. And then submit with whatever even parity nodes are present in the tree. That would give me the answer. In this case, from this even parity node, there were 2 other even parity, same color, basically same color nodes present in the tree one. So from there, I calculated 2. And from the max of odd and even parity, I got a 2. So that 2 plus 2 gave me 4. The second example also, from B, there was no similar color present. There was one similar color present, but it was not directly. And this was again 2. So the answer was 2. In this way, we are going to solve this problem in optimal time complexity of order of n plus m. Pre-calculations would be a BFS here with order of n time complexity, order of m time complexity. And then it's just basic calculations. Overall, let's code it out. Start with getting heads and counts. Function which would return head Even count, so I would first initialize an adjacent subject. First. Then again, pre-populated given queries. Graph view dot append graph v dot append u. Depths I would initialize as 0 first. N. Listed array again initializer with false. While my q equals to text of 0, I'm initializing it. My q visited of 0 as well. Now while my q is not empty, I will remove the node using q dot populate present instance. And then for neighbor using adjacency, just I would get all the neighbors. If any neighbor is not visited, I will increment its depth by 1 visited of neighbor will become 2. I would append this neighbor. Now for even count, I would do sum 140 in depths if p percentage mod of 2 would give me 0. So that means it is an even. That will increment my count by 1. Now odd count would be just n minus even count. I would return depths, even count, and odd count. If one would be length of edges of the plus 1, this would be the number of nodes in there. But we can do whatever else in the depth one, even one, or even I would get using the function get depths and rounds for n1 and edges one. That's two, even two, or we get depths and rounds n2 and edges one. Now max count out of the second tree max of even or whatever parity elements are present at the max. Okay, max count. Now I will create an answer array containing depth. One for this is for tree one. Its color is red or basically it is an even parity. Node count would be even. Every other node at an even distance from the source. Else count would be odd. Insert dot append count plus max down. Return. So let's run this code. Check if it's working properly. Okay, just need to it out. And see the mistake. Missed. Okay, so here was the mistake. Sometimes in graph problems, everything gets mixed up. So it's better to check out your code once again before thinking back on it. Most of the time, it is something written wrongly. Yeah. So it's passing all the test cases. We have solved this weekly contest completely. See the link in description for part one. Thank you. And subscribe to my channel for next weekly contest solutions. Bye bye.